Hello everyone, welcome to today's Tute session, online Tute session, which is designed for off-campus students. However, on-campus students are also welcome to participate if they want to, and also you can watch this recording, the recording of this session later, which I will be making it available to all of the students on the Blackboard sites. Well, for each lecture, normally there is an equation sheet, which I am uploading the equation sheets on the Blackboard sites inside the folder for each of the lectures. It's good to make yourself familiar with the equation sheets. The equation sheets, as you can see here, are very clear. That is, all the equations, all the terms are properly defined, and the units for each of the terms are clearly provided. However, please note that you need to practice on making use of these equations before the exam. It's not just like that at the time of the exam, you take a look at the problem statement and then you find the right equation and do the problem. It just doesn't work that way. I have many years of experience in teaching this unit, and I know that the students who take this approach normally they get no or very little mark in the time of the exam, and this is actually risking the chance of passing the unit as well. So please don't do it that way. Instead, spend time on doing the problems gradually, make yourself familiar with the equations, with the nature of the problems. There are some small points here and there that you've got to take into consideration, and you will not know these points if you don't practice on the problems in your own time at the convenience of your home or anywhere else you are. Well, and also at the time of the exam, the equation sheet that will be given to you will include all the information that are included in these, say, equation sheets, excluding the equation numbers, and of course not in this format, in a concise and compact format. So if you make yourself familiar with the equation sheets, something similar will be given to you, and of course the equation sheet will be provided to you well before the exam, so that you can take a look at it. Then at the time of the exam, you will not have to struggle in order to find the equations, where they are and how to use them. Well, let's get started with the equation sheet. A brief description of the equation sheet. The first equation, equation 1, this one here, is actually a representation of the cycle time when we are talking about manufacturing. Well, when there is a cycle time, that is the time that is taken in order to produce the part. I assume that those who are watching this video or those who are participating in this Tute session have already watched the video for the lecture, the extended video for the lecture. So by the time you are here, you are expected to know some of the terms that will be used in the Tute sessions. If you don't watch the say lecture and then directly come to this Tute session, maybe you don't understand some of the terms that are used in the Tute session. So it is a must to watch the extended recorded lecture and also to participate in the Q&A session that is held on a different time. By the time you come to the Tute session, it is expected that you know some basic concepts. Anyway, moving on. As I said, there is a cycle time, that is the time that is needed in order to produce a part, and that is referred to as TC, and TC has got a number of components. The equation for TC has got a number of components. Those include TO, TH, and TT. TO is the actual processing time, and TH is the time for loading and unloading of the part, that is also referred to as handling time. TT is the time that is needed to replace the cutting tool when it is not to be used anymore. It is blunt and we've got to replace it. And the unit for each of these say time terms is minute per piece. Moving on to equation 1, 2. This equation TB is the time that is needed in order to process one batch of the parts. As we had in the lecture, parts sometimes are produced in the form of batches, and each batch of the parts includes a certain number of parts, say 50, 100, or whatever it is, depending on the size and also on the shape of the part, and also the capabilities of the machining equipment. Well, TB, which stands for batch time, is the time of setup, TSU, plus the time, the fraction, plus the time of process cycle time, TC, which we had up there multiplied to Q. And Q, of course, represents the number of parts in a batch. So there is a setup time, a certain setup time, which applies to the whole parts of the batch. Say, for example, half an hour it takes for us in order to set up the machine. And then we start machining the parts, 100 parts, and say TC is, for example, 5 minutes. We will have 500 minutes for machining plus another half an hour for setting up the machine. So it comes to a total of whatever it is. Well, next equation is the equation for production time. There is a difference between TP and TC. TP takes into consideration the setup time as well. So it indeed TP is equivalent to the cycle time plus the time that is spent on setting up the machine. However, as you can see in this equation, because TP refers to the production time of a single part, we've got to divide setup time by the number of parts in the batch, so that a fraction of the setup time that is used for that given part is taken into consideration. And then RP and RC, we've got two terms that are actually defining the rates of production. RP defines the rate of production, how many parts are produced in an hour for, say, on the basis of production time. And RC does the same, however, what it takes into consideration is cycle time. So RC represents the the rate of production on the basis of cycle time, and RP does the same on the basis of production time. The difference between the two is that in RC, setup time is not taken into consideration, but in RP it is. So it is reasonable to expect that always RC is greater or equal to RP. Okay, now we are done with the terms on rates and also times. There are a number of other equations, and those equations are equations for the cost. And of course, C represents the cost. Equation 1.6 is the one that is used in order to compute the cost of a piece, a unit, or a unit of the workpiece material when it is manufactured. So the cost of manufacturing of a piece of the or one unit of the product is referred to as CPC, and that is equal to a number of components. CM represents the cost of the raw material. We purchase the raw material at a certain cost. It is referred to by CM. At the end of the equation, we've got CT, and that is the cost of tooling, how much we are paying for buying the tool, cutting tool in order to cut the material. And there are some other terms inside. Of course, we know what TP is. There is CL, which stands for labor cost, the wage of the labor machinist who is machining the part, and CQ, which is the representation of equipment cost rate. What is it? If we have a machine, there is a certain cost that is involved in order to run the machine. That is, say, for example, electricity, maintenance, on whatever it is. Well, cost of the material is fixed. Cost of the cutting tool is also, however, for the cost of the labor and cost of the equipment, there are some equations that are given in equations number 1.7 and 1.8. Equation 1.7 represents the hourly rate of the say machinist or labor, which is divided by 16 in order to get it in minutes. And that is also multiplied by another parameter, and that is RLOH, that is the rate of labor overhead cost. And then what is it? If we hire a machinist, it's not just a hourly say wage that we are paying to him. We've got to pay something for superannuation, for some other services that we are providing to the labor. So there is always an overhead cost, and this is often represented in the form of a percentage of RH, and that one sits here. Same for the equipment cost. Again, we've got IC, which is the investment cost, the purchase price of the machine, divided by 60 for the conversion of the units to minute. And then we've got N, which is the representation of the number of years when this machine will be used, say the lifetime of the machine in the term of the years. And H is the number of years, number of hours, number of hours of working in 1 year. And again, we have got an overhead cost, as I said, for running the machine, and that is referred to as ROH. Further down, there's an equation here, down here, which is telling us if we want to produce Q, capital Q, number of quality parts, acceptable parts, how many parts we need to process in order to get this figure. Of course, all of the parts that are being processed will not be acceptable parts in the end of the processing time. Some of them will be scrap parts, and the ones that are scrapped should be taken into consideration. Lowercase q represents the percentage of scrap parts, and when we substitute the percentage of scrap parts, which is achieved on the basis of experience, and substitute all this in this equation, we will get QO or Q0, which is telling us what is the number of starting parts in order to end up in Q acceptable parts. Okay, that was just a quick review of the equation sheet. We need to know the equations when it comes to doing the problems. Now let's move on to doing the doing the problems. That is, say for example here, I have uploaded a number of example problems. Let's look at the example problems first. This is the first example problem. As we can see, let's see what it is asking us to do. It is asking us that a production machine is purchased for an initial cost plus installation that comes to a total of $500,000. It is anticipated that this machine will last for a period of 7 years. So we have purchased it for $500,000 installed, and it is going to work us for 7 years. And then the machine is planned for a 2-shift operation, for a 2-shift operation. In each shift, it will work for 8 hours, and it will work for 5 days in a week. Assuming that there will be 50 working weeks in a year, and assuming that the applicable overhead rate for this equipment is 35% of the initial purchase price, that is 35% of the $500,000, we are to determine the equipment cost rate. What do we do? In order to do this problem, what we need to do is to take a look at the equation sheet and just take the right equation from the equation sheet. What we are going to do is to compute the equipment cost rate, and that is represented in equation 1.8. So what we need to do is to take this equation out and substitute the values that are given in the statement of the problem, and then get the value of CEQ computed. Okay, back to the problem again. So this is what will happen. Indeed, we take this equation out from the equation sheet, this one, and then N is the number, IC is the investment or purchase price of the machine that is given $500,000. We have it. ROH is the overhead cost, and that is given to be equal to 35% or 0.35. N in the equation is the number of years that machine will be working for us, and that is given in the statement of the problem to be equal to 7. And H, the number of hours hours in a year that the machine will be working for us. This is not given, but all the information to have it computed is. So what we do is to multiply 8, that is the number of working hours in a shift, by 2, the number of shifts per day, by 5, the number of working hours in a working days in a week, by 50, the number of, say, working weeks in a year. If we do it this way, multiply all these figures to one another, it comes to a total of 4,000 hours per year. So the value of H is computed to be equal to 4,000. Then what is left to be done is just to substitute all these figures, and this will give us the value of CEQ, and that is equal to $0.402 per minute. This is the cost of running the machine. Still, we haven't included the wage of the labor and some other costs. So what we have computed is just CEQ, the cost of running of the machine without labor. Okay, now let's move on to the next problem. The next problem 1.2. Now it goes a little further. The cycle time and cost per piece. The problem, let's see what problem is telling us. The production machine, example 1.1, the previous example we just had, is used to produce a batch of parts. So there is a batch production. Each has a starting material cost. The starting material cost is given. So what parameters is defining this? The starting work material CM is the parameter that is representing this on the equation sheet. And then batch quantity, or capital Q, is given to be equal to 100. The actual processing time in the operation is given. The actual processing time, or TO, is given is 3.72 minutes. Time to load and unload each workpiece on the machine is 1.6 minutes, and that is handling time, TH. Tool cost is given, CT, and that is equal to $4.4 for each tool, cutting tool. And each tool can be used for 20 pieces before it is finished. So what it means is that for each part, we've got to divide this figure, or the cost of the tooling. For each part, we've got to divide it by the number of parts that are machined by making use of that cutting tool. So 4.40 should be divided by the number of parts, and that is 20. It gives us a fraction of this cost, and that is $2.22 for each workpiece. And the tool replacement takes 2 minutes. So we are machining 20 parts, and then we need a replacement of the cutting tool. So what happens is that this figure, again, these 2 minutes should be divided by the number of parts that are machined after the cutting tool was replaced. So 2 minutes divided by 20 comes to 0.1 minute. That is the actual cutting, that time that is needed for tool replacement for each part. Well, let's continue with the statement of the problem. Before production can begin, the machine must be set up. Of course, we need to set up the machine to put in place the cutting tool, to put in place a fixture if it's needed, adjust the machine, and like that, everything like that, to make it ready for starting the production. But this happens only once in the beginning of production. So the setup time that is given 2.5 hours is again to be divided by the number of parts in the batch, which gives us the setup time for each individual part. Hourly wage rate in the operation is given $16.5, and of course an applicable overhead cost for the labor is also given. 40% of this figure should also be added, which is the overhead cost of the labor. And as I said, this is superannuation, services that the employee is receiving, etc. Now we have to determine in A, the cycle time for the workpiece. In B, average production rate when setup time is figured in. So setup time is to be included, and then we've got to compute the average production rate, which is RP. So the cycle time is TC in part A. In part B, we are after RP. And also the last one, in part C, we've got to compute cost per piece. That is CPC. And that's what we had on the equation sheet. So what do? We simply take out from the equation sheet the equation for this equation. That is the first equation on the equation sheet. We take it out and we substitute the values that are given in the statement of the problem one by one. TO is given up here, 3.72 sits there. And then TH, and that is the handling time, is given up here. It sits in this place. And then in the third place for TT, we've got to substitute tool cost. It is 440, but this is not right to put this figure right here because these, as I said, will be used in order to machine 20 parts and not just one. So we've got to divide it by 20 first, and then what we get, which is 0.1 minute, it will be sitting here. Now TC can be computed for each of the individual parts, which is the cycle time. Well, moving on, again, we've got to compute the average production time per piece, including the effects of the setup time. In order to compute the production rate, which is this equation appears on the equation sheet as I explained in the beginning of the session. This equation, 60 is the number of minutes in 1 hour, and that is used for conversion of the units. TP is the production time, that is the time that is needed to process one part, including setup time. We don't have it. So we take the equation for TP out from the equation sheet. This equation is on the equation sheet. I explained it. We take it out. We insert the value of setup time, the total setup time that was given equal to 2.5 hours divided by the value Q, that is the batch size, and that is 100. And then we add cycle time to this figure. So this is giving us a fraction of the setup time for each part plus the cycle time, TC. And that was computed before in part A. And this will give us the value of TP. Once we have TP at hand, we can easily compute the rate of the production, and that is this much. And in part C of the problem, we've got to compute the cost of each unit of the part, or CPC. We take the equation out from the equation sheet again, and then this is the equation for CPC. So CM is given as the statement of the problem, cost of the raw material. CT is given, and we know that CT that is given has to be divided by 20. So it will be sitting here. CT divided by 20 sits here. And CM, that is the cost of the material for each material, sits here. We have all this information at hand. CQ was just computed because this is the continuation of problem 1.1. It was computed, so we have it. And then TP, we had TP computed. TP sits there as well. And then the only thing that is to be computed is the labor cost, CL. We have the this figure RH, that is the hourly wage of the labor, and that is $16.5. This was given in the statement of the problem. And it was mentioned that we should consider 40% of overhead cost. So 0.40 sits here as well. If we substitute these two values, we can easily get, say, CL. Now CL is also computed. What is left is to substitute the value of CL in this, and then get the cost of a unit of the cost of producing a unit of the product can be easily computed. Okay, moving on. Next problem, it's asking us, a customer has ordered a batch of 1,000 parts to be produced by a machine shop. Historical data indicates that the scrap rate for this type of the parts is %. How many parts should we start with in order to end up in 1,000 quality parts or acceptable parts? Take the last equation out from the equation sheet, substitute the values that are given. Q is given 1,000, and lowercase q, which is the scrap rate, is given to be equal to 4%, and then you can easily compute the value of Q0, and that's the number of parts that we need to start with. So we need to buy this many number of raw materials, that is 1042 instead of 1000, because we want to end up in 1000 quality parts. We need to start with a larger size of raw materials to end up with 1000 acceptable products. Well, technology is not perfect, skill level is not perfect, materials are not perfect, machine tools are not perfect, and these are the reasons why there is always a non-zero scrap rate. Sometimes in the problems, it is mentioned that scrap rate is zero, but in reality, it doesn't happen. Always there is a scrap rate. It could be very small, but it is not a zero. If we want to make it zero, it means that we've got to reach to perfection in everything, and that is not really possible. That's not practical. Okay, and then there is another problem here, which I am leaving it to you. The solution is already on the Blackboard side. So this last problem on the example problems, which is a continuation of what we have been doing so far, I'm leaving it to you. Do it at home in your own time. And if there is a problem, then take a look at the solution to see how you did with this problem. Okay, now let's just close this file, and then we will be moving on to another document, and that is some truth problems. You've got to do the truth problems at home, of course. We do just explain some of them to see how we should be doing the problems. This is an interesting problem. A production machine was purchased 6 years ago for an install price of $530,000. At that time, it was anticipated that the machine would last 10 years and be used 4,000 hours per year. However, it is now in need of major repairs that will cost us $125,000. Well, when we purchased the machine, it was anticipated that it's going to work for 10 years without requiring any major repair. It worked for 6 years, but it didn't happen. Something happened, could be an accident, or said could be the reason. The reason could be the low quality of the machine. It is broken down after some time, after 6 years. Now, if we want to continue using this machine, we've got to repair it, and that is costing us $125,000. If these repairs are made, the machine will be working for another 4 years. So it will end up in 10 years as it was anticipated in the beginning. It will be again operating in the next 4 years for 4,000 hours a year, and applicable overhead cost will be 30%. This is the cost that will be applied to the repair cost. Assuming that the machine will be available 100%, determine the equipment cost rate for this machine. First, machines are not available 100% of the time, because machines need repair, machines need maintenance. So sometimes you've got to stop the machine in order to repair it, change the oil filter if there is one, or change the oil, things like that. However, we can't do this maintenance job at the time when machine is not functioning. Say, for example, there are two working shifts and machine is free for 8 hours. So we can just do the maintenance job at that time, making machine available for 100% of the time. Sometimes it is possible and sometimes it is not. Okay, what we are to do is to compute the equipment cost rate. And of course, what we need to do is to take the equation for the equation cost rate out of the equation sheet that was explained, and then substitute the values and do the computation. So first we take the equation out from the equation sheet. Let me just change this view. Okay. Well, this is the solution. I'm going to explain how it's been done. We take the equation 1/8 out of the equation sheet, and then we substitute the values in it. Of course, initial cost is this much. It was given in the statement of the problem. It was mentioned that it has got some 30% of overhead cost, which sits there, and the machine is going to work for 10 years. That was what we had supposed in the beginning. It will be working for 10 years, and each year there are 4,000 hours of working hours. So you substitute all this, and it gives us an equipment cost rate of this much per minute or this much per hour. And then we just have it computed. However, after 6 years, it needs major repair, and we should consider the cost of major repair as another investment cost, and that is this much. So we make use of this same equation again, equipment cost rate again. This time, instead of the purchase price, what is sitting there is the cost of repair, plus its overhead cost, which was mentioned in the statement of the problem, to be equal to 30%. However, after 6 years of time, if we repair the machine, it will be working for remaining 4 years and not for 10 years. So instead of n of 10, the value of n will be 4. Again, it is mentioned that it will be working for 4,000 hours in a year. So it will be sitting there. It gives us a different CEQ value of this much. Now, for the remaining 4 years, the value of CEQ will change. For the initial, say, for the initial 6 years, the value of CEQ was this much or this much. For the remaining 4 years, the value of CEQ will be greater, and that is the summation of this value and this value, which comes to this much, and that is significantly higher than what it was in the beginning. So the value of CEQ will change for the remaining 4 years, and that is a result of major repair. Okay, now moving on to the next problem. Let me see. Is there any question from the audience? Any question that I need to answer? Please go ahead with your questions. No questions, so we'll continue with the problems. Okay. Instead of repairing, now we are in the workshop. We are thinking about repairing the machine. All of a sudden, someone walks in and is trying to convince us to buy a brand new machine instead of repairing the old machine, coming with a proposal that I am going to actually sell you a brand new machine for your job. Don't waste your money on the repair job. Instead, buy a brand new machine, which is going to cost you this much. How much it is going to cost us? It's going to cost us $700,000 installed, the new machine. But instead of 4 years, it will be working for you for another 10 years, brand new machine. And there is an overhead cost of 30%, this much. An overhead cost of 30% for the brand new machine, this much. It will be again working for you for 4,000 hours a year for 10 years time. However, this brand new machine will be working for you faster than the old machine because it has got a better technology. It is making it possible for you to produce 20% more of parts in an hour. You are producing more parts in an hour by 20% because of the capabilities of the new machine. And also, we know that we are buying the raw material for each part, for producing each product for this price, and we are selling the process parts for this price. This is the other information that is given. If the scrap rate is zero, and machine is available 100% of the time. Now the question is that, what is the best option for us? To proceed with the repair job, repair the old machine for $125,000 and make it work for another 4 years. After that, scrap the machine and buy a brand new machine, or just scrap the machine right now and buy a new machine, and it will be working for next 10 years for you, and it will be giving you 20% more production in an hour or in a year. Which one is a better option? What do we do? What we need to do for this problem is to do the computation of the profit in the next 4 years. But two different scenarios. Scenario one, to repair the old machine, and then because we have the purchase price of the raw material and the sale price of the product, we can compute how much profit we are making for producing each one of the parts. Then we compute how much profit we are making if we make use of the old machine and repair it against how much profit we will be making if we buy the new machine. Then compare the two figures with one another, and that will telling you which one is a better option for you. And if we want to do that, what we have to do is to this is what we already had done before. We had computed this. Now knowing that the labor cost is $24, that is given in the statement of the problem. If we know the labor cost, which is equal to this much, then what we need to do is to do the computation of the profit that will be made in 1 year if we repair the old machine. This is the profit that we will be making if we repair the old machine against the profit that we will be achieving if we repair the machine, if we buy the new machine, and it's this much. Which one is greater? The one that is greater is the option that we will be going for it. And that is obviously if we buy the new machine. He's giving us more profit. We are making more profit if we buy the new machine and do not repair the old machine. So we will go for the new machine on the basis of this scenario. Scenario may change and you may end up that you've got to repair the old machine. So in different situations, of course, different solutions, different results will be achieved. Okay. Now the question is that what happens if the new machine becomes idle after 4 years? What do? We do not know, because we think that this new machine is going to work us for 10 years without requiring any major repair. Maybe after 4 years time, we cannot sell the product that we are producing. So this machine will be useless because this machine is only able to produce this given part. What do we do? If this is the case, then in the equation for computation of the CEQ of the new machine, what we need to do is to substitute this value of 10 by 4, and that will giving us a higher value of CEQ. So if you are told that after 10 years, after 4 years, the contract of you with the one who is buying the products will be over and there will be no new order coming to you. Even if you buy the new machine, it will be used only for 4 years, and after that it will be useless. So what we need to do is to substitute this value of 10 by 4, and then it will give us a new value for CEQ, and it will affect all the computations. So do it again, and then you will make a decision whether or not you should be repairing the old machine or buying the new machine. So if the story changes, everything will be affected. Okay. Any questions on this? Okay. Well, there is another problem which I have uploaded on the Blackboard, and I am leaving it to you to do the next problem. We have already gone over one. We have already been running this for 40 minutes, and there is actually some time left, but I don't want to do the other problem. I want you to practice on the other problem. Solution will be uploaded. So do the problems, even the ones that we discuss, do them at home, in your comfort at home, and make sure that you know how to do the problems. You've got to practice on doing the problems. When you look at the solution, it looks easy. When you want to do it yourself, it's the time when you face questions and problems. And if you do it gradually over the semester, gradually spending a few hours every week on this course, you will find it a very enjoyable and easy to understand unit. But if you leave everything to the end of the semester, it won't be an easy unit to do. Okay, any questions? Okay, I have got only one, and now we have got 2 people. Okay, any questions? I'm going to conclude the session. Is there any question? Please ask your questions. Otherwise, I would like to thank you for your participation. And this session is being recorded. I will upload the recording for your future reference. Any questions? Are you and also Sabine? Any questions? Assignments. There will be no are you off-campus student? You are, right? For on-campus students, there will be two reports, lab reports, and one, yes, off-campus. For on-campus students, there will be actually, let me stop recording.